Spacetime is spoken of as if it were the stage upon which existence plays its endless drama. Yet in truth, it is no stage at all, but an invisible ocean stretching in every direction without surface or shore. Across its unseen waters drift galaxies like luminous ships, while every planet, every heartbeat, every fleeting thought is carried along by currents no eye can witness. To the senses it feels solid and dependable, a steady rhythm of ticking clocks and fixed distances. But beneath its calm lies a fabric alive with ripples and folds, waves of gravity racing across the dark like whispers from ancient collisions of stars. It is a veil stretched delicately across nothingness, a skin of order pulled tight against the abyss. The haunting question arises: is this veil truly fundamental, or is it only a shadow, a painted surface concealing something deeper still? Physicists peer beneath its weave, searching for the loom upon which reality is stitched. Every theory bends toward the same abyss, that space-time may not be the final truth, but an illusion rising from structures more abstract than geometry, more elusive than time. And so the search continues, not merely for equations, but for meaning. For what lies beneath the fabric of space-time may not only redefine physics, it may redefine what it means to exist at all. If you are new here, join the journey, like, subscribe, and let's begin. In the quiet dawn of the 20th century, the universe was still imagined as a stage A stage, vast and unmoving, upon which the motions of planets and stars were choreographed like celestial dancers in Newton's grand performance. Space was an emptiness, a silent container, an infinite box in which matter drifted. Time was an arrow, straight and absolute, ticking evenly from past to future, untouched by the events it measured for nearly 3 centuries. This view had endured, its certainty binding the world of science. Newton had declared gravity a force, a mysterious attraction pulling bodies together. Across the void, it was a vision, elegant enough to guide the paths of cannonballs and comets, reliable enough to place a man upon the moon centuries later. Yet within the equations of the old order, there were cracks, subtle, almost imperceptible strains in the fabric of certainty. At the turn of the century, a young clerk in a Swiss patent office began to see beyond that static stage. Albert Einstein, restless and unbound by academic tradition, asked a question no one had dared. What if space and time were not separate at all? What if they were not background, but actors? Not passive, but alive? By 1915, his insight crystallized into a vision that would overturn the very notion of reality, general relativity. Here, gravity was no longer a mysterious pull, but the bending of space and time themselves. Matter did not sit within space. It told space how to curve space. In turn, told matter how to move planets traced not invisible lines of attraction, but the elegant curves of geometry itself. It was a revelation as poetic as it was scientific. The universe was not built upon a rigid stage, but upon a fabric. Soft, malleable, dynamic stars, planets, even light itself were caught in its weaving. The cosmos had become a living tapestry. The shock was profound. For centuries, gravity had been a force, invisible yet certain. Now it dissolved into something stranger, something more intimate. Reality itself was geometry, and geometry could bend, stretch, ripple. But great ideas demand proof, and Einstein's new world was fragile, precarious in the absence of evidence. It was in the spring of 1919 that a chance alignment of Earth, Moon, and Sun offered a rare stage upon which to test it. A total solar eclipse, when the Sun's light would be briefly extinguished, and the stars near its edge could be seen in the darkness of midday sky. Arthur Eddington, an English astronomer, set out to catch this fleeting shadow on film. If Einstein was right, the Sun's immense mass would bend space-time around it, and starlight grazing its surface would curve ever so slightly. Newton's gravity predicted one measure of deflection. Einstein's geometry predicted another, a difference small, but decisive. A fingerprint of the fabric on the island of Principe, off the coast of Africa, and in Sobral, Brazil. Telescopes strained toward the darkened sun. The photographs were blurred, imperfect, blurred further by clouds and weather. Yet within the grain of the plates was the faint, undeniable signal the stars had shifted, bent by the sun's presence exactly as Einstein had foretold. The fabric was real news, rippled across the world with the same weight as the discovery itself, the revolution in science. declared the Times of London Einstein's equations were no longer mathematics, but truth written in the sky. Humanity had glimpsed for the first time that the universe was not built on emptiness, but on something supple, something that could stretch and fold. The birth of this fabric changed everything. It reshaped the map of the cosmos, turning it from static stage to restless sea. It suggested that space itself could swell or shrink. That time itself could flow at different rates, depending on the contours it passed through. It opened doors to black holes, to an expanding universe, to ripples that would someday be heard as gravitational waves. It revealed that even the vacuum is not empty, that reality has texture, and with that, a new kind of wonder took root, not the wonder of distant planets circling in perfect orbits, but the wonder of a universe alive at its core. The stage had collapsed into the play itself, the backdrop had become the actor, and the birth of space-time as fabric marked the beginning of one of humanity's most profound journeys. The search to understand what lies beneath it, the triumph of general relativity, had given humanity a new vision of the universe, a cosmos, sculpted not by invisible forces but by the curvature of space and time themselves. Yet even as Einstein's fabric spread its shadow across astronomy, another revolution was unfolding on scales far smaller than the eye or the telescope could see in laboratories across Europe. Physicists confronted a reality more elusive, more unsettling than anything revealed by the bending of starlight. Electrons refused to trace neat orbits around atomic nuclei. Light, once imagined as a wave, began to reveal itself as quanta, discrete packets of energy, as if the universe itself spoke in syllables, rather than in a flowing stream. Matter and energy blurred together, obeying laws that seemed less like geometry and more like riddles. This was the birth of quantum mechanics, a framework not of curves and continua, but of probabilities, uncertainties, and sudden leaps. It was a new kind of whisper, faint yet undeniable, rising from beneath the fabric of space-time. Niels Bohr, Werner Heisenberg, and Paul Dirac gave these whispers their first mathematical form. Bohr's principle of complementarity declared that particles and waves were not separate things, but dual aspects of the same underlying truth. Heisenberg's uncertainty principle told of a boundary written into nature itself. That position and momentum could never be known with absolute precision. Dirac merged quantum theory with relativity, predicting the existence of antimatter, a mirror form of matter born directly from the equations. These were not minor adjustments, but revelations that reality was woven from threads finer and stranger than geometry alone. While Einstein's universe curved gracefully on cosmic scales, the quantum realm trembled with jittering fields and restless energies, as though the very ground of reality were alive. The two visions coexisted. Uneasily, general relativity explained the heavens with majestic certainty. Quantum mechanics unraveled the atom with unsettling accuracy, but when the two were brought together, they clashed like oil and water at ordinary scales. The contradiction could be ignored. A planet circling a star could be modeled by relativity. An electron bound to a nucleus could be modeled by quantum mechanics, but at the edges, where the very large collapsed into the very small, the dissonance grew impossible to silence. Physicists soon realized that both frameworks, so powerful on their own, were incomplete. Relativity described spacetime as a smooth continuum, a fabric that could stretch without limit, curve without tearing. Quantum mechanics suggested otherwise. At unimaginably small distances, at the Planck scale, 10 to the minus 35 meters, smoothness may dissolve into something rough, granular, or foamy. Here, spacetime might not be a continuous fabric at all, but a seething ocean of uncertainty, bubbling with quantum fluctuations. Distances themselves may flicker, geometry may fluctuate, time may stutter. The fabric itself may unravel into a froth where meaning blurs. This possibility haunted both theorists and philosophers. If space-time was not continuous, then relativity's elegant stage was only an approximation, a vast and convincing illusion, dissolving under a closer gaze. What appeared smooth from afar could, beneath, be jagged. What seemed eternal could, beneath, be fleeting. Einstein resisted these whispers to the end of his life. He doubted the completeness of quantum mechanics, calling its randomness an impossibility, declaring that God does not play dice with the universe bore countered, insisting that reality itself may be written in probabilities rather than certainties between them. The debate raged, a dialogue not only between men, but between visions of existence itself, yet experiments sided with the quantum. The double-slit experiment revealed that even single particles could interfere like waves. As though aware of all possible paths at once, quantum tunneling allowed particles to slip through barriers, as if space itself could momentarily dissolve, entanglement-bound distant particles in correlations so tight that distance seemed irrelevant, defying Einstein's insistence on locality. Each discovery deepened the fracture between the two great pillars of physics. One described spacetime as a majestic fabric, bending smoothly under the weight of mass and energy. The other whispered that beneath this fabric lay a restless ocean, a lattice of probabilities, a realm without certainty. Physicists searched for reconciliation, yet every attempt seemed to fracture the picture further. Renormalization was devised to tame infinities in quantum field theory, yet gravity resisted all such cures. Spacetime, when treated quantum mechanically, refused to remain stable, collapsing into violent fluctuations at the smallest scales. The unease grew into a realization. Relativity and quantum mechanics were not two views of the same world, but two halves of a broken mirror. Neither complete, neither false, each whispering truths that the other could not bear. What lurks beneath the fabric of spacetime began to appear less like smooth cloth and more like a tapestry woven of contradictions. Perhaps the fabric was an emergent illusion, a macroscopic order rising from microscopic chaos. Perhaps time itself, so steady in relativity, was only a shadow cast by a deeper, timeless quantum reality. The Planck scale became both a boundary and a frontier. Here, units of length and time collapsed into indivisible quanta, marking the point where current theories fail beyond it. Human understanding falters, a veil drawn tightly across the heart of reality. This uneasy truce between the large and the small has endured for a century. Relativity rules the stars, galaxies, and the curvature of the cosmos. Quantum mechanics rules atoms, molecules, and the restless dance of particles. But where they meet, at black holes, at the birth of the universe, at the threshold of the Planck realm, their union dissolves into paradox. It is here, at this boundary, that the whispers grow louder, not the whispers of certainty, but of possibility, that beneath the fabric may lie not geometry but a new order, unimagined and unspoken, a realm where time and space are not fundamental, but consequences loom, invisible still. Weaving both relativity and quantum into patterns humanity has only begun to glimpse. And so, the fabric trembles with two voices, one smooth, one fractured, a harmony unresolved, a song unfinished, waiting for the day it will be heard as one. There are places in the universe where the fabric of space-time bends so violently that it can no longer hold together, places where geometry itself caves inward, where distance collapses and time twists upon itself. These are the black holes, the darkest scars upon the cosmic cloth, predicted first by Einstein's equations. They were once dismissed as mathematical curiosities, unreal solutions to an otherwise elegant theory, but nature is indifferent to human disbelief. In the hearts of dying stars, when nuclear fire fails and gravity is left unopposed, collapse becomes inevitable. The stellar core falls inward, shrinking without mercy, pressing atoms into densities beyond imagination. And in that collapse, a black hole is born. At its edge lies the event horizon, a boundary not of matter but of no return, a line in space-time where escape becomes impossible, where not even light can flee. To an outside observer, in falling matter appears to slow, stretched across the horizon as if frozen in time. But from within, there is no halt, only descent, a plunge deeper and deeper into curved space, toward the hidden singularity at the center. Here lies the first tier in the fabric. A singularity is not a place in space, but the end of space itself, a point where density climbs to infinity, where Einstein's equations surrender, collapsing into contradictions. It is not matter that breaks here, but space-time itself. Physicists speak of singularities with reverence and unease, for they mark the limit of knowledge. At their heart lies the question, does the universe conceal realms where its own laws dissolve? Are singularities real, or simply warnings, signs that a deeper theory must exist, one that rewrites the foundations of reality. For decades, black holes remained hidden in mathematics, veiled by their own darkness, but observations revealed their presence through their influence. The fierce pull on companion stars, the jets of high-energy particles expelled from their fringes, the gravitational waves rippling out when two collide. No longer were they abstractions, but real engines of the cosmos, sculpting galaxies, stirring matter, and seeding questions deeper than any before. It was in the 1970s that black holes revealed their most haunting whisper. Stephen Hawking, blending relativity with quantum theory, discovered that these objects are not perfectly black at all. At the event horizon, quantum fluctuations of the vacuum allow particle pairs to appear. Normally, they annihilate in an instant, returning their energy to the void, but near the horizon, one particle may fall inward while the other escapes outward, to an observer far away. It seems as though the black hole itself is radiating heat, Hawking radiation, a trickle so faint it has never been observed directly, yet inescapable in its implications. It means that black holes are not eternal prisons. They evaporate, losing mass over immense timescales, until eventually they may vanish into nothing. This revelation tore deeper into the cloth, for if a black hole evaporates, what happens to the information carried by the matter it consumed? Quantum mechanics insists that information cannot be destroyed. Relativity seems indifferent. Hawking's discovery appeared to suggest annihilation, a violation of one of the most sacred laws of physics. The information paradox was born. It has haunted physics ever since, a riddle at the border of spacetime and quantum law. Is information somehow encoded in the radiation itself? Does it leak out in subtle correlations invisible to current tools? Or does the horizon conceal a firewall, a searing boundary that obliterates anything that falls within, rewriting even the principles of relativity? Each possibility demands a sacrifice, either of Einstein's smooth fabric or of quantum mechanics' strict unitarity. Neither side can be surrendered without consequence. It is as if black holes have been placed in the universe as riddles, forcing humanity to peer beyond the fabric towards something deeper. Observations sharpened the mystery rather than resolved it. In 2019, the Event Horizon Telescope delivered the first image of a black hole's silhouette, a luminous ring encircling darkness in the galaxy M87. What it revealed was both confirmation and question. The shadow matched Einstein's predictions with uncanny precision, yet behind that precision lurks the unresolved paradox of information, a silence waiting beyond the horizon. Theorists speculate that space-time itself may be emergent, rising from networks of quantum entanglement. If so, the singularity is not the destruction of the fabric, but the edge of its applicability, a place where the deeper loom beneath space-time becomes exposed. Others imagine that black holes may be gateways, their interiors connected by wormholes to distant regions of the universe, though such bridges may be unstable and fleeting. Still others propose that information is stored upon the horizon itself, encoded as a hologram upon the very boundary where light is trapped. Each theory whispers of something beneath, of a level of order unseen, of a structure deeper than space-time. But no experiment has yet pierced the horizon to reveal the truth. Black holes remain both wound and window-wound, because they shred the equations of relativity at their cores, mocking the smooth fabric that Einstein revealed window, because through their paradoxes, they hint at the unfinished nature of physics, pointing beyond both relativity and quantum theory, toward a synthesis yet unknown. The first tears in the cloth remind humanity that its greatest theories are only approximations, shadows of a deeper reality still hidden, and in those tears, one can almost glimpse what lurks beneath, a loom not of curves and forces, but of something stranger, something that may weave both geometry and quantum law into one unseen pattern. For a century, Einstein's equations had whispered of a strange consequence. If space-time were truly a fabric, then violent motions of mass should send ripples through it. Faint waves stretching outward, carrying information about the cataclysm that produced them, like the trembling of a drum when struck. The universe itself should resonate when stars collide, when black holes merge, when titanic events unfold in the dark. Yet for decades, these ripples remained a ghostly prediction, too faint, too elusive to touch. Search began in earnest in the late 20th century. Physicists dreamed of an instrument sensitive enough to feel distortions. In space smaller than the width of a proton, they imagined colossal interferometers, beams of laser light, stretched down vacuum tunnels kilometers long, reflected between mirrors, capable of detecting the slightest shift in distance caused by a passing wave of gravity. The ambition bordered on the impossible, for the signals would be vanishingly small, drowned by the noise of the Earth itself, by tremors, by traffic, by the motion of air. But still the dream persisted, for if detected, these waves would confirm the last great untested prediction of general relativity and open a new sense with which to perceive the cosmos. In 2015. The Laser Interferometer, Gravitational Wave Observatory, LIGO, stirred in its long silence. On September 14th, two black holes spiraled together in a galaxy over 1 billion light-years away. Their dance quickened, their horizons touched, and in that instant of merging, a fraction of a sun's mass was converted to pure gravitational energy, radiating outward as ripples in spacetime. 7 milliseconds later, those ripples reached Earth through the vacuum arms of LIGO's detectors in Louisiana and Washington. Spacetime itself stretched and compressed, shifting the laser beams by less than 1/10,000th the width of a proton. It was an almost imperceptible shiver, yet unmistakable, the first direct detection of gravitational waves. A soundless chime in the fabric of reality, it was as if the universe had spoken for the first time in a new language, and humanity had finally learned to listen. The signal matched Einstein's prediction with eerie precision. The rising frequency and amplitude of two black holes spiraling to collision, the final ringing tone as the newborn black hole settled into silence. It was both a triumph of theory and a beginning of something larger. For the first time, scientists were not only seeing the cosmos, but hearing its structure. The implications were profound. Gravitational waves revealed a universe invisible to light. Where telescopes show the glow of stars and galaxies, gravitational waves expose the silent mergers of black holes, the collisions of neutron stars, the convulsions of the early cosmos. They offer a way to look past the veil of electromagnetic radiation, to glimpse epochs and events that no light can escape. Yet with the triumph came deeper questions. What medium carries these waves? If spacetime is fabric, are these ripples disturbances in the cloth itself, or echoes of something beneath it? In ordinary waves, on water, or in air, the medium can be studied, touched, understood. But spacetime is intangible, unseen. To detect its trembling is to confirm its reality, yet still not to know its substance. The poetic tension lingers. Humanity has learned to hear the surface of the ocean, but remains blind to the depths from which its swells arise. Gravitational waves tell us that spacetime is elastic, but not why it exists, nor from what it is woven. The detections multiplied in the years that followed. Dozens of black hole mergers, each adding new notes to the cosmic symphony, the collision of neutron stars, producing not only gravitational waves, but a burst of light and heavy elements, witnessed by telescopes across the world. Gold, platinum, and other heavy atoms forged in that furnace now rest in rings and crowns, in circuitry and bone, a reminder that the whispers of spacetime are tied to the matter of life itself. And yet, beyond the celebration of discovery, the philosophical unease grows deeper. The waves prove that Einstein's fabric is real, but they also remind us of its fragility. For every ripple is a reminder that spacetime is not absolute, not rigid, but mutable, stretching and compressing with the events of the cosmos. It is not the empty void Newton once imagined, but something that can be stirred, something alive with motion. Some theorists imagine that by mapping gravitational waves with exquisite precision, hints of quantum structure might appear, small, irregularities that betray the granularity of spacetime. At the Planck scale, others suggest that these waves could carry imprints from the earliest instance after the Big Bang, when the universe itself shuddered into existence, encoding a record of what lies beneath the visible cosmos. The detectors of today are only the first instruments, sensitive enough to hear nearby collisions, but not yet the murmurs of creation itself. New generations are being built. LISA, a constellation of spacecraft planned to float in deep space, separated by millions of kilometers, listening for waves of lower frequencies that Earth-bound observatories cannot detect. Einstein telescopes and cosmic detectors may one day hear the faint hum of the early universe, or reveal deviations from relativity that point toward a deeper law beneath. Until then, every detection is both answer and question, proof that spacetime trembles, yet silence about what it truly is, confirmation of Einstein's vision, yet mystery about the loom upon which his fabric is stretched. To listen to gravitational waves is to hear the heartbeat of the cosmos. But like hearing the ocean in a shell, one senses that the sound is only the surface of something vaster. Something hidden beneath the ripples lies an ocean uncharted. And beneath that, perhaps, the first whispers of what spacetime itself emerges from. The waves arrive as faint murmurs across billions of light years. Yet they carry a message both scientific and philosophical, that the universe is not still, not silent, not fixed. That reality itself can ring like a bell, that the fabric upon which existence unfolds is not only a stage, but a voice calling out from the depths of time, and in that voice, humanity is left to wonder, if space-time can sing, what greater music waits beneath it unheard? For centuries, the void was imagined as absence, a backdrop without substance, a hollow silence against which matter and energy played their roles. In Newton's time, the vacuum was emptiness itself, an infinite stage unmarked by motion or change. But the 20th century would reveal a stranger truth. What appears empty is never still. In the framework of quantum field theory, the vacuum is not a barren void, but a restless sea. Every point of space is alive with fields, invisible scaffolds of reality. And those fields never rest. They tremble, they fluctuate, they conjure particles into being, and erase them again in instants too brief to measure. What was once thought to be nothing is now understood as the most dynamic something of all. These fleeting apparitions are called virtual particles. Pairs of particle and antiparticle emerge from the fabric, live for a heartbeat of Planck time, and then annihilate, leaving no trace but a whisper of energy. It is a restless froth, a ceaseless churning that underlies the solidity of the world. Physicists speak of it as zero-point energy, the lowest possible energy of a field, which cannot be removed, no matter how cold, no matter how empty. Even at absolute zero, space still seethes with fluctuation. This vision is not mere speculation. It leaves fingerprints in reality itself. In the mid-20th century, Dutch physicist Hendrik Casimir proposed a daring prediction. If two metal plates are placed exceedingly close together, the restless vacuum outside them will exert a subtle pressure, squeezing the plates inward. The cause lies in the virtual waves that fit, or fail to fit, between them. Some modes are excluded, others allowed, and the imbalance produces a measurable force. Years later, this Casimir effect was confirmed in laboratories. No particles were exchanged, no photons fired, yet the plates shifted, drawn together by the silent insistence of the vacuum. It was proof that the emptiness around us is no emptiness at all, but a field alive with hidden pressure. Such discoveries unsettle the imagination. For if nothing is never nothing, then the ground of existence is stranger than myth. The very space between galaxies, between atoms, between thoughts, is alive with activity beyond sight. It is as though reality breathes in a frequency too fine for human senses, whispering in the margins of matter. This restless vacuum is not only a curiosity of theory, its energy may be written into the cosmos itself. Quantum fluctuations in the early universe are believed to have seeded the large-scale structure of galaxies. Tiny variations in the foam of the vacuum were stretched by cosmic inflation to astronomical size, sculpting the cosmic web of clusters and voids that now spans the sky. The stars themselves may owe their arrangement to the play of particles that never truly existed. Yet the vacuum also poses one of the most troubling paradoxes. In modern physics, according to quantum field calculations, the energy density of the vacuum should be enormous, perhaps 120 orders of magnitude larger than what astronomers measure in the expansion of the cosmos. This mismatch, sometimes called the worst theoretical prediction in science, suggests that something is missing from our understanding. Either the fields cancel in ways we cannot yet describe, or there is a deeper layer beneath the fabric, hiding the true origin of this energy. Some speculate that the vacuum energy is tied to dark energy, the mysterious pressure that drives the accelerating expansion of the universe? If so, then the fate of the cosmos is being written in the restless silence of the void. Every distant supernova, every receding galaxy, may be a reflection of what nothingness truly is. Others take the puzzle further. Perhaps the vacuum is not only alive with fluctuations, but fundamental. Perhaps space-time itself emerges from this restless sea, woven from entanglements of quantum information in the void. In this view, what appears as geometry may be the shadow of deeper relations, the loom upon which Einstein's fabric is stretched. If so, then listening to the vacuum may be the first clue to what lies beneath space-time. The question grows haunting. If emptiness itself is alive, what does that mean for the concept of reality? Is the universe built upon a foundation of nothing that is everything? Is matter simply a crest on the foam of the vacuum, a temporary shape in a sea that never rests? In the laboratory, scientists continue to probe the invisible pressure of the void. In the cosmos, astronomers measure the faint fingerprints of its energy in the motion of galaxies and the afterglow of the Big Bang. But no measurement has yet revealed why the vacuum has the value it does, nor whether it is stable for eternity. The possibility lingers that the vacuum of today is not the ultimate vacuum, but a false ground, as a metastable state that could, in some inconceivable future, decay to a deeper nothingness, rewriting the laws of physics in an instant. The thought chills, that the stage of existence itself is impermanent, that the void is not a bedrock but a veil. And yet, in its restless motion, the vacuum also offers a kind of beauty. It is proof that silence is never silent, that stillness is never still, that the most profound mysteries lie not in distant galaxies or hidden black holes, but in the invisible spaces all around, within every breath and every atom. The quantum vacuum is not absence, but presence disguised, a fabric that hums with invisible notes, a sea without surface, a loom upon which space-time itself may be woven. It is a reminder that the universe is deeper than sight, that even nothingness is a story, alive with whispers too faint for human ears, and in those whispers may lie the key to the final layer of reality, the loom beneath the cloth, the silence that is never still. In the late years of the 20th century, astronomers sought only to measure the slowing of the cosmos. Gravity, they believed, should gradually tug upon the expansion left by the Big Bang. Decelerating the great outward rush of galaxies, the universe might coast forever, or collapse in some distant cataclysm. But it could not accelerate. That possibility was unthinkable, and yet, in 1998, the sky told a different story. Two independent teams of astronomers peered across billions of light years, observing the light of ancient supernovae, dying stars whose explosions served as standard candles, their brightness revealing cosmic distances. What they found was astonishing. The farthest supernovae appeared dimmer than expected, as if the galaxies that held them had slipped farther away than any model could explain. The cosmos was not slowing. It was speeding up. In that moment, the universe revealed a secret force woven into its very fabric, a repulsive energy pervading all of space, driving galaxies apart with invisible hands. It was given a simple name: dark energy, a name that captures only its ignorance, not its essence. The discovery was a shockwave through physics. For nearly a century, Einstein's general relativity had been the trusted guide, predicting expansion, curvature, and the delicate dance of space-time. Einstein himself had once inserted a constant, the cosmological constant, to allow for a static universe. When expansion was discovered, he called it his greatest blunder, and yet, in 1998, that abandoned constant returned as prophecy. A simple term in the equations of space-time could explain the acceleration, a uniform energy of the vacuum itself, woven evenly throughout the cosmos. But the simplicity concealed a deeper terror when physicists calculated the energy density of the quantum vacuum, the restless sea of virtual particles. The result was catastrophic. The predicted value exceeded the observed energy of the cosmos by 120 orders of magnitude, a number so vast that it has been called the worst prediction in the history of physics. Why does the vacuum not crush space-time with its overwhelming energy? Why is the universe expanding slowly, not exploding with unbearable force? This riddle is known as the cosmological constant problem, a wound at the heart of modern science. It suggests that our theories of quantum fields and relativity cannot both be complete. Some delicate balance, some hidden cancellation must be at work. Yet no one knows why as telescopes scan deeper. The scale of the mystery grew. Dark energy is not a minor correction, it is the dominant component of the cosmos, composing nearly 70% of its total energy budget. Galaxies, stars, planets, and life itself account for less than 5%. All that is familiar is outweighed by the pressure of an unknown force, silent yet sovereign. The very geometry of destiny is written by a presence that cannot be touched or seen. Some imagine dark energy as a property of space itself, a constant hum of the vacuum. Others speculate it is dynamic, evolving through time. A quintessence, a field that shifts and flows, whispering across the ages. If so, it could change. And with it, the fate of the cosmos could be rewritten. Observations from missions such as WMAP and Planck have sharpened the picture, mapping the subtle patterns in the cosmic microwave background. They reveal a universe flat on the largest scales, stretched and expanded under the rule of dark energy. But they do not reveal its nature, like a shadow without a body. Dark energy shows itself only through its effect on spacetime's growth. And so the question turns philosophical. If spacetime is a fabric, then dark energy may be the tension woven into its threads. A pressure from beneath the weave, an echo from a deeper loom. Could it be that dark energy is not an addition to the cosmos, but the signature of the layer beneath spacetime itself? A sign that the vacuum is not merely restless, but creative, generating expansion from nothingness. The haunting possibility arises. Perhaps the universe is not stable. Perhaps our cosmic acceleration is only a phase, destined to change or collapse when the vacuum itself finds a new balance. If dark energy shifts, galaxies could be torn apart in a big rip, every atom stretched beyond recognition. Or it might fade, allowing gravity once more to dominate, pulling everything back into a final collapse. Between these extremes lies an eternal acceleration, a cold, lonely future where galaxies vanish beyond horizons, leaving only silence. Dark energy forces humanity to confront the fragility of understanding. The cosmos is not the quiet mechanism once imagined, but a stage shaped by invisible hands. The expansion we measure is a riddle written into the heart of space-time. Each galaxy that recedes is a message, each photon a clue, yet the code remains unbroken in 1998. The universe whispered a truth no one expected, that the fabric of space-time is not passive, not still, but alive with a hidden force. It accelerates, it pushes, it writes the story of destiny with a pen no human has yet seen. And behind that whisper lies a deeper question. Is dark energy a property of this fabric, or a shadow of the reality beneath it? The discovery of acceleration was not an answer, but an opening. A reminder that the greatest mysteries of the cosmos are not in distant galaxies alone, but in the emptiness between them, that the void itself holds secrets powerful enough to dictate the fate of all things. And in its silence, the universe reminds us that what lurks beneath the fabric of space-time may yet be stranger than any dream. In the mid-20th century, black holes seemed like silent voids, swallowing all memory of what crossed their horizons. No signal could return, no story could escape. But then a troubling whisper arose from the mathematics. The entropy of a black hole, its measure of disorder, was not infinite, but finite and proportional not to its volume, but to the area of its surface. Jacob Bekenstein, and later Stephen Hawking, revealed this startling fact: a black hole does not erase information entirely, but encodes it upon its boundary. Its surface area becomes a ledger of lost histories, measured in units as small as the Planck length each. A bit of information pressed into the horizon like ink upon a page of night. This was the first hint of something profound, that the universe may not store its secrets in the depths of volume, but on the surfaces that bound it. That reality itself may be holographic. The idea was sharpened by physicists Gerard 't Hooft and Leonard Susskind. They suggested that the information needed to describe a region of space is not contained within, but encoded on its boundary like a hologram, a three-dimensional image woven from a two-dimensional sheet of interference patterns. What seems like depth is an illusion, a projection from a hidden script written on the edges of being, and then came a breakthrough that gave flesh to the whisper in 1997. Juan Maldacena proposed the ADAS-CFT correspondence, a startling equivalence between two seemingly different worlds of physics. On one side, a gravitational universe curved by the rules of Einstein, living in a higher dimensional space. On the other, a quantum field theory without gravity, etched on the boundary of that space. The two were not separate, but reflections of each other. Gravity and space-time themselves emerged as a holographic shadow of quantum information. It was as though reality had revealed a trick of mirrors. What feels like the fabric of space, the flow of time, the weight of mass, might all be illusions projected from a deeper language. Not matter, not energy, but information, the pure currency of existence if true. The implications are unsettling. Every galaxy may be a holographic image, every black hole a vault of encoded data, the universe itself a vast screen, playing out a drama written in symbols no human eye can see. And yet, in its strangeness, the holographic principle offers a reconciliation. The rift between quantum mechanics and relativity, long a wound in physics, softens if spacetime is emergent quantum entanglement. The ghostly link between particles may weave the very threads of geometry. The fabric may not be fundamental at all, but the byproduct of information binding itself into order. Some physicists now speak of spacetime as a construct of entanglement, a network of quantum links whose tapestry gives rise to distance, curvature, and gravity. In this vision, the universe is less like a stage and more like a song, harmony emerging from invisible notes of information projected into the illusion of space and time. But the whisper cuts deeper still. If the universe is a hologram, then what lurks beneath the fabric may not be physical at all. It may be a code, a lattice of information beyond matter, beyond fields, beyond any tangible substance, a hidden script that writes the stars and the silence between them. This possibility stirs philosophical unease. For if reality is a projection, what then is the source? If spacetime is a shadow, where is the light that casts it? If galaxies are images, what is the screen upon which they are displayed? The holographic whisper suggests that what humanity calls real may be only a surface, a veil stretched thin over deeper truth, that the universe is both more fragile and more profound than imagined. A cosmos woven not from atoms or waves, but from meaning itself, encoded in structures that defy vision. And so, the search for what lies beneath space-time circles back to an ancient question. Is reality made of things or of patterns? Is the universe built from substance or from knowledge? Black holes, once feared as destroyers of information, may in fact be the scribes of the cosmos. Their horizons are pages, their entropy is language, and in their whispers lies the hint that the universe is not what it seems. The holographic principle is not yet proven. It is a speculation, a framework, a suggestion whispered through equations and symmetry. But it offers a glimpse of a truth that could unite gravity with quantum mechanics, space-time with entanglement, geometry with information. It suggests that the answer to what lurks beneath the fabric may not be hidden in particles or waves, but in the quiet pulse of information itself. The fabric may be a veil, the universe a projection, and beneath it, only the code remains, silent, eternal, unseen, yet writing the story of all that is. In the silence of mathematics, two visions emerged, both daring to suggest that space-time, the very fabric of existence, is not fundamental, but woven from threads unseen. The first vision was string theory. It began with a simple idea that the smallest building blocks of nature are not point-like particles, but tiny vibrating strings. Each vibration, each mode of oscillation, gives rise to what humanity perceives as a particle A. Photon is one note, an electron another, a quark still another. Matter and force, mass and energy, all become music on strings too fine to see. These strings demand dimensions beyond the familiar four of space and time to be consistent. They must vibrate in a higher dimensional arena, where hidden dimensions curl upon themselves at scales smaller than any microscope can probe. Calabi-Yau manifolds, intricate shapes folded into the fabric, may be the silent halls where these vibrations echo. The universe perceived by human senses may be only a shadow, cast by motions in spaces unseen. Yet string theory is not only a theory of matter, it is a theory of gravity itself. Among its vibrations lives a special mode, the graviton, the quantum of gravity, suggesting that gravity is not separate, but born from the same string as all else in its symmetry. String theory offers the possibility of unification, a single song from which the cosmos is composed. But the theory is vast, almost infinite in its possibilities. Its landscapes of solutions number in the trillions, each describing a different potential universe. Which of these corresponds to reality remains unknown. The strings hum, but their music has not yet been heard in experiment. The second vision arose in a different key-loop quantum gravity. Instead of smoothing spacetime into strings, it imagines spacetime itself as granular. The continuum of Einstein's fabric dissolves into discrete quanta. Loops of geometry that weave together like a cosmic chainmail area and volume become quantized. Indivisible units no smaller than the Planck scale. At this scale, spacetime is not smooth, but woven from loops, a lattice of finite pieces giving rise to the illusion of continuity in this vision. Black hole entropy emerges naturally. Horizon area is counted in quanta of surface, tiny patches that sum to the ledger, discovered by Bekenstein and Hawking. The singularities at the hearts of black holes and at the origin of the Big Bang may be softened by this discreteness. Where relativity predicts infinities, loops impose limits, replacing catastrophic collapse with rebirth. Both string theory and loop quantum gravity reach toward the same haunting suggestion: that spacetime is not the final layer, but emergent, that what humanity perceives as the flowing fabric of reality is woven from structures deeper still, whether vibrations of strings in hidden dimensions or loops of finite geometry beneath the continuum. These frameworks, though different, share a poetic weight. They suggest that existence is woven on scales too fine for sight, too delicate for touch, that every step, every breath, every galaxy turning is played upon threads smaller than imagination can hold. Yet neither vision is complete. String theory has elegance but little experimental anchor. Loop quantum gravity captures geometry, but struggles to embrace matter. Both remain unfinished symphonies, whispers of a loom yet unseen. Still, they remind humanity of a humbling truth, that the fabric trusted to carry stars and memory may not be fabric at all, that beneath the visible lies a deeper weave, unseen but essential. Perhaps one day, experiments will hear the faint vibration of a string, or glimpse the granularity of space in gravitational waves finer than any yet measured. Perhaps the loom will be revealed, and the fabric traced to its threads. But for now, the search continues, guided by mathematics, intuition, and the restless need to know in the end. Both visions return to a single poetic reflection, that humanity itself may be woven from threads too fine to see, that thought and time, memory and motion are born from vibrations or loops beyond perception. That life is not only in the fabric, but of the fabric, written in the same script as galaxies and stars strings, and loops are more than theories. They are metaphors of existence. They whisper that beneath space-time lies a loom, a hidden architecture, delicate, eternal, and still unknown. And on that loom, the story of the universe is woven, one thread at a time, in patterns yet unseen. At the heart of physics lies a boundary, a veil so fine it escapes all microscopes, yet so absolute that no equation can pass through unchanged. It is called the Planck scale, a length of 10 to the power of minus 35 meters beyond it. Classical spacetime dissolves into something unknown at this inconceivably small scale. The smooth fabric described by Einstein can no longer be trusted. Distances blur, time itself flickers, and the geometry of the cosmos fractures into quantum uncertainty. Here, gravity and quantum mechanics, long estranged, must finally meet. But when their equations are combined, infinities arise, contradictions multiply, and the laws of physics collapse upon themselves. This collapse marks the Planck wall, a boundary of knowledge rather than matter. It is not a wall built of stone or light, but of mathematics itself. Every attempt to peer beyond, it ends in paradox. It is the horizon of human. Understanding physicists have tried to approach the wall through thought experiments and simulations. Imagine compressing energy into a region smaller than the Planck length gravity would overwhelm. twisting space-time into a black hole before any observation could be made. Attempts to probe beneath the veil lead only to shadows of collapse. The wall defends itself. Some have wondered if space-time is not fundamental, but a phase of matter, emergent, like ice condensing from liquid water. In this vision, what appears continuous and immutable may in fact be the result of deeper constituents arranging themselves into a pattern beneath the Planck wall. Space-time could melt away, revealing new states of reality beyond geometry. Beyond distance and duration, hints of this possibility arise in theories of quantum gravity. Loop quantum gravity suggests space-time is woven from finite quanta, indivisible loops of area and volume. String theory whispers that what humans perceive as particles are vibrations of filaments hidden in dimensions folded beyond perception. In each case, the Planck scale marks not the end, but the beginning of a deeper structure. The wall is not a termination, but a threshold. Yet no experiment can yet test these ideas. Particle accelerators fall short by magnitudes of magnitude. Even the collisions of cosmic rays, more powerful than any machine, cannot resolve scales so small. The Planck wall remains impenetrable, unbroken by either observation or calculation still. Its presence shapes the way science dreams. It sets the ultimate limit to what can be measured directly. It whispers that there are truths humanity may never witness. Only infer. It reminds that all knowledge is provisional, bounded by the walls of perception and technology, and yet, like all walls, it tempts imagination what lies beyond the Planck veil. Some speculate it is a boiling sea of quantum foam, where space-time surges and collapses in constant turmoil. Tiny wormholes open and vanish. Dimensions twist upon themselves, and causality itself becomes uncertain. Others suggest a lattice, a digital grid beneath the flow, as though the universe is coded rather than continuous. And still others believe the veil conceals a state beyond physics, where the very notion of space no longer applies, whatever truth lies there. The Planck wall is more than a boundary in science. It is a mirror of human limitation. To stand before it is to recognize the frailty of equations, the finitude of the senses, and the humility of reason. It is to feel the same awe as ancient stargazers who stared into the night sky, knowing there were realms they could never reach. The Planck wall is not the end of curiosity, it is the spark that keeps it alive. For every boundary is an invitation. Every veil is a call to look closer, to imagine deeper, to risk equations that may fail in order to glimpse what might lie beyond in this way. The Planck wall is not an obstacle, but a promise that the universe still holds mysteries vast enough to resist the reach of intellect, that the loom of reality, whatever its true form, remains hidden just beyond the veil, and that humanity, standing at the edge of knowledge, will continue to wonder, to calculate, and to dream. For now, the Planck wall remains unbroken, a frontier not of matter, but of meaning. A reminder that beneath the smallest scales, where time and space dissolve, there may be truths so alien they can only be whispered in metaphor. And yet, within that silence lies the most human of discoveries, that the very act of reaching, of imagining what lies beyond the wall, is part of what it means to exist. In the long search for the foundations of reality, one question lingers like a shadow. Is the universe stable, or is it perched precariously upon a hidden precipice, balanced on a plateau that could one day give way? Quantum field theory suggests that what is called the vacuum, the ground state of all fields, the stage upon which particles play, may not be the true ground at all. Instead, it could be a false vacuum, a temporary minimum of energy, not the ultimate resting place of the cosmos. If so, then reality itself is fragile, held in a metastable state, awaiting collapse into something deeper. This collapse would not resemble the slow erosion of stars or the patient cooling of galaxies. It would happen in an instant. A bubble of lower energy vacuum could appear at any point in space, seeded by quantum fluctuation or by a rare, violent event. Once formed, it would expand at the speed of light, rewriting the laws of physics as it spread. No warning could outrun it, no shelter could resist it. Inside this bubble, particles as known today would lose their identity. Forces could shift, atoms could disintegrate, and chemistry itself might be extinguished. The familiar constants, the strengths of interaction, the very scaffolding of matter would be erased. To those living within the current vacuum, it would appear not as an explosion, but as sudden silence, the annihilation of the old script, replaced by a new one, alien and absolute. This is not speculation born of fantasy, but of calculation. In 2012, measurements of the Higgs boson's mass suggested a troubling implication. Its value placed our universe near the border between stability and metastability. If the numbers are correct, the vacuum of today may not be the lowest possible energy state. We may inhabit a plateau, with a true valley hidden beneath it, and the abyss between them waits silently. The timescales are vast. Theoretical estimates stretch beyond the lifespans of stars, beyond the evaporation of black holes. Trillions upon trillions of years may pass before any bubble emerges. And yet, the possibility is there, woven into the mathematics itself. The threat is both infinitesimal and absolute. Physicists call this scenario false vacuum decay. Its strangeness lies not only in its lethality, but in its indifference. It does not depend on human action, nor on cosmic catastrophe. It is the quiet fragility of existence itself, coded into the structure of fields and energy. The sword of Damocles, suspended not above civilizations, but above the fabric of space-time. Some imagine this false vacuum as part of a wider energy landscape, a terrain of hills and valleys, where different pockets of reality settle into different rules. In this picture, universes are not unique, but scattered across a multiverse of possibilities, some stable, some unstable, each shaped by the plateau upon which its vacuum rests. Our cosmos may simply be one region among countless others, perched on a ridge that will someday crumble. To contemplate this is to feel the profound vulnerability of being. Not only is life fragile, not only are planets and stars destined to fade, reality itself may be temporary, a provisional arrangement in a deeper architecture we cannot yet see. And yet, there is a strange comfort hidden within the dread. For if vacuum decay lies ahead, it comes without pain, without forewarning. Without resistance, no observer could ever witness its arrival, for the bubble horizon would erase consciousness faster than thought. It is destruction beyond terror, because terror itself would never arise. Still, the philosophical weight remains. To live in a metastable universe is to exist on borrowed certainty, to be a structure rising from quicksand, unaware of the abyss below. It reframes the cosmos not as a fortress of permanence, but as a fragile bloom, beautiful precisely because it will not last. For physicists, the false vacuum is both a nightmare and a guide. It forces deeper questions about the nature of fields, the meaning of stability, and the possibility of new physics beyond the standard model. It demands answers that may only be found at energies forever out of reach. It turns the search for truth into a confrontation with impermanence. Whether the vacuum is true or false, stable or unstable, may never be fully known. Perhaps the universe is safe upon its plateau, destined only for cold expansion into eternity. Perhaps it is not safe at all, and one day, far beyond memory, a silent wave will erase the familiar script and begin another. The abyss remains, a whisper beneath equations, a reminder that even space-time itself may not endure. And so, humanity stands where it always has, at the edge of mystery, staring into a fabric that could one day unravel, haunted by the thought that the ground beneath its feet is not the floor of reality, but only a fragile ledge above the abyss. In the early visions of physics, the universe was imagined as a stage filled with particles, forces, and fields, little actors upon a backdrop, governed by laws written into the geometry of space-time. But in the 21st century, a new whisper began to rise in the halls of theory. A whisper that suggested the backdrop itself may not exist as matter or energy, but as something more elusive, that what lies beneath the fabric of reality may not be substance. But quantum information theory grew not from the cosmos, but from the laboratories of computation. It began as a study of how qubits, the quantum siblings of bits, behave when entangled, measured and manipulated, and yet its implications spread far beyond the dreams of building quantum computers. For the mathematics of information began to mirror the mathematics of space-time itself, suggesting that the threads of the universe may be woven not from particles or strings, but from relationships, from networks of entanglement that bind the cosmos together. One of the most audacious insights came from the work of Juan Maldacena in 1997. He proposed that a universe with Gravity, a curved space-time like our own, could be exactly equivalent to a universe without gravity, but filled with quantum fields upon a flat surface. This was the ADS-CFT correspondence, a bridge between geometry and quantum theory. It hinted that space-time might not be fundamental, but emergent, that the three-dimensional world, with its stars and distances, could be a hologram, projected from a two-dimensional surface encoded with quantum information. The idea soon deepened with a provocative equation. ER, proposed by Leonard Susskind and Juan Maldacena. It suggested that wormholes, known in relativity as Einstein-Rosen bridges, might be nothing other than quantum entanglement itself. Two particles, entangled across vast distances, could in some sense be joined by a thread of space-time if true. The very glue of the universe is not geometry, but correlation reality held together by shared information. Entanglement, once dismissed as a mathematical oddity, becomes in this view the loom upon which space-time is woven. Each quantum link a stitch, each correlation a tie, binding the fabric into coherence. The geometry of the cosmos might be nothing more than the large-scale shadow of countless invisible relationships. What appears to us as distance, curvature, and gravity could be the macroscopic echo of information flowing in patterns too fine for direct perception. This vision unsettles, for it shifts the ground beneath physics. Matter dissolves into energy, energy into fields, and now fields into code. What remains is not substance, but structure, not things, but the way things are related. The essence of existence becomes the logic of interaction, the choreography of entanglement. Such an interpretation carries poetic weight. It imagines the universe not as a machine, nor as a stage, but as a computation not running on silicon nor on gears, but on the raw fabric of quantum states. Every atom, every photon, every gravitational wave, nothing but an entry in a cosmic calculation, a universe thinking itself into being. And yet, mysteries remain. If space-time emerges from information, then where does information reside? Is it contained in the universe, or is the universe contained in it? Does the code run on a substrate still deeper than fields and qubits, a foundation forever hidden? Physicists pursue these questions through tensor networks, through simulations of entanglement lattices that produce emergent geometry. Mathematics shows that space, with its distances and volumes, can rise naturally from webs of information. Even Einstein's equations of general relativity can emerge from the thermodynamics of entanglement, as though the universe itself were whispering its secret. I am not made of matter. I am made of meaning. This is the cosmic code. A code not written in symbols upon paper, nor carved into stone, but inscribed in the pattern of reality itself. It is the silent script that shapes the stage, the hidden music that arranges the stars. And if one listens closely, the question grows louder. Is the universe not merely alive, but aware of its own structure? Is existence the act of self-computation, the cosmos dreaming its own form into reality? At the threshold of this thought, science meets philosophy. The distinction between physics and metaphysics blurs, and the pursuit of equations becomes the pursuit of meaning itself. Beneath space-time may not lie particles, fields, or even energy. Beneath space-time may lie the grammar of existence, code, pure and unbroken, writing reality with each passing instant. And so, the journey into the fabric leads not to the solidity of matter, but to the abstraction of relationship, not to the permanence of ground, but to the fluidity of logic. The final veil suggests that we are creatures living not upon a material foundation, but within a poem written in the language of information, a poem that the universe endlessly composes as it thinks itself into being. At the frontier of knowledge, science becomes an act of patience and daring. The questions now are not small, and neither are the tools required to pursue them, for what humanity seeks is nothing less than the secret stitching of space-time itself, the attempt to glimpse the loom on which reality is woven. Particle colliders, telescopes, detectors, and quantum simulators stand as instruments of this pursuit, each one designed to probe for subtle hints that space-time is not the final layer, but the surface of something deeper. At CERN, the Large Hadron Collider continues to smash protons together at energies once confined to the first moments after the Big Bang. Its discovery of the Higgs boson in 2012 was a triumph, but also a revelation of fragility. For the mass of the Higgs hinted that our universe rests uncomfortably close to instability, a false vacuum poised upon a knife's edge, and so physicists push further, searching for deviations, anomalies, the faint fingerprints of quantum gravity hidden within the chaos of collisions. If space-time is emergent, then the smallest scales, far beyond the precision of current machines, may reveal its unraveling. Other eyes look not inward, but outward into the deep sky. The cosmic microwave background carries the first light of the universe, stretched and cooled across 13.8 billion years. Its faint irregularities, mapped in exquisite detail by missions like WMAP and Planck, contain the fossilized memory of creation. In those ripples lie clues to the origin of space-time itself. Were they seeded by inflation, a burst of expansion driven by fields unknown, or are they the scars of deeper processes, signatures of a fabric not fundamental but emergent? Future instruments aim to push even further, to measure polarization patterns in that ancient light, seeking whispers of primordial gravitational waves. Such signals would be the fingerprints of the universe being born, and perhaps the first proof that space-time itself had to be woven into existence on Earth. New detectors rise from the soil like cathedrals of science. The proposed Einstein telescope, buried deep beneath European mountains, will listen for gravitational waves across a range of frequencies beyond LIGO's reach in orbit. The Laser Interferometer Space Antenna, or LISA, is planned to float on arms millions of kilometers long, detecting the slow ripples from colliding supermassive black holes. These instruments are not merely observatories. They are stethoscopes pressed to the chest of space-time, listening for the rhythm of its hidden machinery. Yet, perhaps the most profound experiments do not measure the heavens at all, but simulate them in miniature in laboratories. Physicists craft quantum simulators, artificial lattices of atoms and photons, arranged to mimic the equations of quantum field theory in these systems. Space-time-like behavior can emerge from the dance of entanglement alone. If geometry can rise within glass and lasers, then perhaps the cosmos itself is but a grander version of the same. These tabletop experiments whisper a possibility once confined to philosophy, that the universe is not built, but computed. Each of these efforts, whether particle collider, telescope, or simulator, is a hand tugging at the veil. Each seeks a loose thread in the fabric, hoping to pull it gently and glimpse the loom beneath. Perhaps the veil will reveal discreteness where continuity was assumed. Perhaps space-time will show itself not as smooth, but as granular, pixelated at the Planck scale. Perhaps gravity, long the holdout against quantization, will finally betray its hidden quantum nature in subtle deviations from Einstein's perfect curves. And yet, none of this is guaranteed. It may be that the energies required to see space-time unravel lie forever beyond human reach. It may be that the deepest truths remain hidden, written in a code too fine for any detector to grasp. But still, the pursuit continues, for science is not only the act of knowing, but the act of seeking at the edge of colliders, telescopes, and simulations. Humanity is not merely measuring, but listening. Listening for the tremor in the silence, the irregularity in the pattern, the breath beneath the surface. For if space-time is emergent, then somewhere in its weave there must be seams. And through those seams, if they can be found, the universe may whisper the story of what lies beneath. It is here, at the limits of technology and imagination, that physics transforms into philosophy. Each collision, each photon, each vibration in a laser beam is a question posed to the abyss, and each absence of an answer is a reminder that the abyss is vast. The experiments continue nonetheless, not out of certainty, but out of necessity. For to tug at the veil is to be human. To wonder what lies beyond is to fulfill the oldest dream of thought. And so, at the edge, humanity waits, eyes on the stars, machines tuned to silence, minds searching the noise, pulling gently at the threads, hoping the fabric of space-time will reveal its hidden loom. And with it, the secret of what truly lies beneath. In the cathedral of modern physics, two pillars stand unshaken. One is quantum mechanics, the language of the small, where particles blur into waves and probability rules like a sovereign king. The other is general relativity, the geometry of the vast, where space-time bends, curves, and enfolds matter in its embrace. Each is flawless within its own dominion. Quantum mechanics predicts the behavior of electrons, photons, and atoms with a precision so great that no experiment has ever defied it. Relativity explains the orbit of planets, the dance of galaxies, the fall of stars into black holes, all with a calm inevitability that has never failed, and yet, the two cannot touch without breaking at first glance. It seems they should embrace both as stories of the same universe, told at different scales. But when their equations are brought together, the harmony dissolves into discord. Relativity demands smoothness, a continuous fabric where space and time can be divided infinitely. Quantum theory insists on granularity, a world where uncertainty reigns and discreteness defines the smallest scales. Each is consistent, each is true, and yet together they cannot coexist. Decades of effort have tried to heal this fracture. Physicists have ventured into string theory, where particles are imagined not as points, but as vibrating strings, whose resonances generate the tapestry of matter and force. They have proposed loop quantum gravity, where spacetime itself is woven from discrete loops. Like threads in an unseen weave, other approaches attempt to reconcile the clash by suggesting spacetime is emergent, a pattern arising from quantum entanglement rather than a fundamental stage on which events unfold. But each attempt, when pressed for prediction, meets resistance. String theory stretches into dimensions that may never be tested. Loop quantum gravity remains elegant but incomplete, its mathematics unable to recover the full grandeur of Einstein's curves, and the dream of space-time as emergent remains more philosophy than experiment. Tantalizing but unproven everywhere the theories touch. Contradictions spill forth to describe the singularity inside a black hole. Relativity predicts infinities, curvatures without limit, densities without end. Quantum mechanics rejects infinities outright, demanding that probabilities remain finite and calculable. At the edge of the Big Bang, relativity paints a cosmos born from a singular point, while quantum theory insists the uncertainty principle must smear this origin into something softer, stranger, perhaps eternal. The closer science looks beneath space-time, the more elusive the truth becomes. It is as if the loom withdraws at the moment we reach for it, the threads of reality retreating deeper into shadow. Each collision of ideas, each clash of equations, deepens the mystery rather than resolves it. This escalation is not failure, but revelation. For the incompatibility itself is a message. It says that our vision is partial, our tools incomplete, that the universe is not bound by the neatness of human mathematics, but by a deeper order not yet glimpsed. The history of science has seen such fractures before. Classical mechanics, once thought final, shattered under the discovery of quantum principles. Newton's law of gravitation, elegant as it was, yielded to Einstein's geometry of space-time. Each contradiction then, as now, was not an end, but a signpost. Perhaps the same is true here. Perhaps the discord between quantum theory and relativity is itself the compass, pointing toward what lies beyond. The search continues. As colliders, telescopes, and simulators probe at the very edges of this rift, physicists now suspect that black holes may hold the key, objects so extreme that both quantum mechanics and relativity must apply. Together, the paradox of information loss in black holes, debated for decades, remains one of the most pressing tests of unification. Does information vanish with the collapse of matter, violating the sacred law of quantum conservation? Or does it survive, encoded somehow on the horizon, a message written across space-time itself? To answer this is to decide whether the universe is knowable by the rules we have, or whether new laws must be born. And so, escalation continues. Every theory advanced, every framework proposed, carries within it both promise and collapse, like rival empires sharing a contested border. Quantum theory and relativity clash where their dominions overlap. The battlefield is not only mathematical, but conceptual. Does reality arise from geometry or probability? Is time fundamental or merely emergent? Is space-time a stage or the play itself? Each attempt to unify ends not in certainty, but in a deeper fog. The loom retreats, the threads slip away, and yet the pursuit does not end. For within the contradictions lies the most profound truth of all, that the universe, in its deepest structure, remains unfinished to the human mind, and that the act of reaching, of colliding theories against each other, is itself the fire that lights the way forward. In this clash of ideas, physics becomes more than science. It becomes philosophy, poetry, and faith in the unknown. The closer humanity looks, the more the loom withdraws, and still we reach. For centuries, the universe has been pictured as a stage of vast arena of space and time, upon which the actors of matter and energy move and collide. It has been the canvas of every equation, the silent backdrop of every law, but in the quiet halls of modern physics, a radical thought has taken root. What if the stage itself is an illusion? What if space-time is not fundamental, but something that emerges, like a mirage upon a desert plain? The suggestion comes not from poetry, but from the fractures between our greatest theories. General relativity describes space-time as a smooth, continuous fabric. Quantum mechanics insists that reality is granular, probabilistic, woven from discrete events. The contradiction grows sharper at the smallest scales, where neither picture can be trusted completely. The closer physicists look, the less certain the very existence of space-time becomes. In this tension, a new vision arises. Emergent space-time here. Geometry is not primary but secondary. Distance, direction, even the flow of time are not building blocks but consequences. They emerge from patterns of quantum entanglement, the invisible connections that link particles across the cosmos. Studies in quantum information theory have shown hints of this strange possibility. In certain toy models, networks of entanglement can produce the same equations that describe the curvature of space-time in relativity, as if the threads of quantum correlation, when woven tightly enough, conjure the very fabric in which stars and galaxies are set. One radical conjecture, known as ER or EPR, suggests that wormholes and entanglement are not merely related, but identical in essence, that the invisible bonds between quantum particles may be the same phenomenon as the tunnels relativity permits through space-time. If so, then space itself could be nothing more than a vast web of relationships. A tapestry with no fabric, only the threads of connection. The idea unsettles the foundations of reality. If space-time is emergent, then what lies beneath? If the distances we measure, the durations we live through, the coordinates we map, are not elemental truths but derived appearances, then reality must be stranger than any geometry can describe. Some physicists propose that beneath space-time lies an abstract sea of quantum information. A landscape not of points and lines, but of bits, qubits, and algebraic patterns. In this vision, the universe does not exist in space and time. Instead, space and time are the shadows cast by deeper structures, unseen yet inexhaustibly real. This picture finds resonance in the holographic principle, a conjecture born from black hole thermodynamics. And refined through string theory, it proposes that everything within a region of space can be described by information, encoded on its boundary, that the three-dimensional world may itself be a projection from data, inscribed on a distant surface. If true, then space-time is not the foundation, but the projection, a film cast from a deeper real. Yet such theories provoke as much unease as wonder. For if space-time is not real, what then is real? If the river of time is but an emergent current, then what is the bedrock on which existence flows? Are human lives, rooted in the passage of days and the distances of places, no more than illusions spun from hidden symmetries? Here, physics collides with philosophy. The possibility that space-time is not fundamental threatens the very language by which reality is described. To say that something emerges is to suggest a source more primary, but no, consensus exists on what that source might be. Is it quantum entanglement? Quantum computation? A still undiscovered framework beyond mathematics itself? Experiments strain at the edges for clues. Gravitational wave detectors, such as LIGO and Virgo, test the smoothness of space-time with exquisite precision. Quantum simulators built from ultra-cold atoms attempt to mimic the birth of geometry from entangled states. Astronomers map the cosmic microwave background, searching for subtle imprints of pre-geometric origins in the afterglow of the Big Bang. Yet, so far, the veil holds, and still, the idea grows, for it answers riddles that space-time alone could not. It explains why black hole horizons scale with area, not volume, as though space itself were not the true repository of information. It explains why entanglement, the most non-local feature of quantum theory, seems to underpin the continuity of space itself. Without entanglement, space-time may unravel into nothingness. The implications are profound. If space-time is emergent, then the universe is not a container, but a conversation. Reality becomes not a substance, but a relationship, not a stage, but a script written in the language of connection. In such a picture, we are not objects moving through space and time. We are patterns woven into a loom without fabric, illusions, perhaps, but illusions with structure, coherence, and meaning. It is a vision that unsettles, but also inspires, for it suggests that the true essence of the cosmos may not be distance or duration, but information and relation, that beneath every horizon, every clock, every map, lies a deeper order that is not spatial, not temporal, but something else entirely. And so, the question lingers, if space-time is not real, what then is real? If the cosmos is an emergent tapestry, what hand or what law does the weaving? The loom remains hidden, the threads unseen, and humanity, perched at the edge of knowledge, gazes into the abyss where space-time itself may not exist, and wonders if, in that abyss, the truest reality waits to be revealed. At the edge of physics, where equations lose their grip and language begins to fracture, a deeper silence waits. It is not the silence of space nor the silence of time, but the silence of foundations. The moment when reality itself begins to dissolve into question. If space-time is not fundamental, what then is existence? If geometry and chronology are not the pillars of the cosmos, but shadows of something else, then the very idea of being trembles on uncertain ground. The challenge is not only scientific, but philosophical. For every measurement taken, every experiment designed rests on an assumption that time ticks forward, that distances can be measured, that space exists to be traversed. But if these are not elemental truths, then the instruments of science themselves may be measuring illusions. The ruler and the clock may be nothing more than tools for navigating a dream. Physicists wrestle with the problem in their laboratories, but its echoes reach back across centuries of thought. Plato once told of a cave where prisoners mistook shadows for the world itself. They saw only flickering projections upon stone walls, never the fire that cast them, nor the reality beyond. So too, modern science wonders if humanity is bound in its own cavern, mistaking space-time for the totality of being, when in truth it may be no more than a projection. The idea unsettles because time is the medium of human life. Every heartbeat, every memory, every hope depends upon its flow. If time is emergent, if it is not fundamental but derivative, then what becomes of a life measured in hours and years? Does mortality itself dissolve into illusion, or is illusion all that mortality has ever been? Quantum gravity researchers offer possibilities that read like parables. In some models, time is not a river but an eddy, a local current within a wider sea of timeless relations. In others, change is fundamental, but time is not. Motion exists, but the clock is an afterthought. There may be events, but no universal order of before and after. In such visions, the past and future lose their solidity, and the present becomes a fragile construct of perception. The abyss deepens when ancient metaphors align with modern theory. Hindu cosmologies once spoke of Maya, the world as illusion, veiling a truer reality. Buddhist texts reflected on impermanence, the fleeting quality of phenomena that appear solid yet are not now. In physics, space-time itself shows signs of being impermanent, not eternal stage, but transient mirage. And yet, in the heart of this abyss, there is also a strange beauty, for illusions, though not fundamental, are not meaningless. The rainbow is an illusion of light and water, yet it is real enough to behold. The horizon is a mirage of curvature, yet it guides the traveler onward. So too, space-time may be illusion, but it is the illusion that gives rise to galaxies, to stars, to life and consciousness. It may not be ultimate, but it is indispensable. The philosophical weight is almost spiritual. For the closer science peers beneath reality, the more reality begins to resemble a dream. A dream structured, coherent, mathematical, but a dream nonetheless. Perhaps the truest description of existence is not as a machine or a stage, but as a story unfolding in the mind of the cosmos itself. Still, questions press harder. If time is not real, what becomes of destiny? If space is not real, what becomes of separation? If causality itself dissolves, then what does it mean to say that one thing gives rise to another? The abyss does not only threaten science, but meaning itself. Some philosophers suggest that the dissolution of spacetime forces a new definition of reality, that what is real is not what exists in time and space, but what persists across frameworks, the invariants, the relations, the structures that endure no matter what description is chosen. In this light, reality is not objects but patterns, not matter, but mathematics, not a stage, but a symmetry. Others see in this dissolution a return to mystery, that the further science advances, the more it circles back to questions once thought metaphysical. What is the nature of being? Why is there something rather than nothing? What lies beyond the shadows on the wall? And yet, perhaps the shadows are all that will ever be seen. For if space-time is illusion, it is an illusion of extraordinary power, one that has held stars in their orbits for billions of years, one that has guided humanity from firelight to telescopes peering at the edge of the cosmos. The abyss may never be crossed, but the shadows themselves may be the only reality needed. As the 20th century gave birth to relativity and quantum mechanics, physicists dreamed of unification. Now, in the 21st, the dream has transformed. The task is no longer simply to join two theories, but to question the very ground upon which all theories are built. The abyss has widened, but so too has the horizon of possibility at its edge. A haunting realization emerges that perhaps there is no ground at all, that reality is not a foundation, but an endless cascade of emergences, each layer giving rise to the next. With no final bedrock beneath in such a vision, truth itself becomes a horizon, forever receding, forever beyond reach here. Science meets philosophy, and both dissolve into wonder. Perhaps existence is not a puzzle to be solved, but a mystery to be lived. Perhaps the abyss is not a void to fear, but a mirror, reflecting back the strangeness of being itself. And so, at the brink of knowledge, humanity gazes into the philosophical abyss. Time flickers, space trembles, and reality itself seems to whisper. The closer you come, the less you know. The dream deepens. The shadows dance, and somewhere, beyond the veil of space-time, the fire still burns unseen. At the end of inquiry, when equations falter and metaphors strain, all that remains is the fabric itself. Space-time, the silent loom stretched across the cosmos, the stage upon which every galaxy drifts, every star burns, every life begins and ends. For more than a century, it has been both compass and mystery, guiding the trajectory of science while withholding its deepest nature. Now, after relativity and quantum theory, after black holes and gravitational waves, after whispers of holograms and shadows of strings, the loom appears less certain than ever. Its threads seem thin, its weave unstable, as though it conceals more than it reveals. Perhaps it is not the foundation of reality, but a veil stretched taut across an abyss no mind can yet name. Humanity stands before this loom as weavers of questions. Each experiment, each equation, each telescope turned toward the stars is a shuttle cast into the dark. The answers gathered are threads, but they do not complete the cloth. Instead, they fray its edges, revealing glimpses of something beyond. Not particles, not waves, not even fields, but something stranger than comprehension allows. The abyss beneath space-time is not hostile, but it is silent. It yields no hint of its depth, no echo of its nature, and yet, in that silence lies meaning, for a mystery unresolved is not emptiness, but possibility. It is the open horizon that drives inquiry forward, the shadow that gives form to light. The philosophers of old spoke of nothingness as terror, the void from which existence recoils, but physics whispers a subtler truth that nothingness may not be absence at all, but potential, the raw, unshaped possibility from which existence itself is born. Not matter, not energy, not geometry, but the capacity for all of these to arise. A loom not woven of threads, but of the very potential to weave in this vision. The abyss beneath space-time is not a void to be feared, but a womb of creation. Every fluctuation, every emergence, every law of physics may be no more than the surface ripples of a deeper ocean of possibility. An ocean that does not move, does not flow, does not exist in time, yet from which all time and movement are born. Humanity's role within this unfolding remains uncertain. We are, perhaps Perhaps only shadows on the wall of Plato's cave, tracing patterns upon the veil. Or perhaps we are threads ourselves, woven into the loom, each consciousness a knot in the larger tapestry. Either way, the mystery defines us. For it is not the answers we hold that shape us, but the questions we cannot yet resolve. The unresolved silence of space-time is, in truth, the measure of human identity. We are not creatures of certainty, but of wonder, not beings of knowledge, but of seeking. The loom of nothingness is not only the architecture of reality, it is the mirror in which humanity glimpses its own reflection. So the story closes not with a solution, but with an opening. The deeper science peers into the fabric of reality, the more it reveals the abyss beneath, and the closer the abyss comes into view, the more it whispers of something beyond even science. The unspoken, the ineffable, the dream that gives rise to the dream. Perhaps then, what lurks beneath space-time is not a thing at all, not a particle, not a field, not a geometry or code, but possibility itself, the pure potential from which stars ignite, from which galaxies whirl, from which thought awakens to wonder. In this possibility lies the quiet poetry of existence. A universe woven not from certainty, but from openness, a cosmos whose truest law may not be mechanics or symmetry, but the unending invitation to question. And so, the loom remains, stretched across the abyss, shimmering with galaxies, rippling with waves of time. Its threads are fragile, its weave unfinished, but it endures not as a final truth, but as the beginning of every question yet to come. The abyss beneath remains silent, but in that silence, the human story finds its voice.